So I'd like to introduce Marco Milo from Dell. He'll be providing the next presentation. Marco.
Thank you, Brian. Good afternoon, everyone, you the brave. And my name is Marco Milo, and I am from the pre-sales EMEA organization at Dell. And during this session, I would like to give a little bit of an overview regarding the challenges of large-scale HPC and AI systems and how a new range of form factors are emerging to address those needs. So if we move this way, okay, going straight to the point of the problem, these are the growth predictions for CPU-intensive and GPU-intensive workloads in terms of power density per rack unit. These, as you can see, are the forecasts from 2023, and we were projecting to reach the 8 kilowatts per rack unit for the GPU-intensive workloads and the 5 kilowatts per CPU-intensive workloads. 1 year later, we have revised those estimates, and the forecast seems to be pretty much on par, and even the curve seems to overlap quite nicely. But the problem is that basically the scale is doubled. So what does that mean? This means that we're basically doubling down on the forecast, and by 2033 we might reach the 16 kilowatts per rack unit in case of GPU-intensive workloads, and around 7 kilowatts for CPU-intensive workloads. If you think those numbers are massive and impressive, and if we translate those numbers in the typical 48-unit HPC rack, this projects an estimate around 750 and 800 kilowatts per rack. So you understand the size of the problem. So this is clearly an extrapolation, so it can be subject to errors and little variations, but it's still important to set the stage and let us understand the directions we are taking, where we are going. The concern is that we are approaching to a tipping point where the laws of physics will basically give a checkmate to the traditional way we have operate and designed the systems in a large-scale data center. We're facing many issues connected with the component miniaturization, power, cooling, and moving forward, further improvements will still be possible, but will require more and more efforts, and the more we improve, the harder it will become to make more progress. So this is where the Open Compute project plays a key role, because it's a vibrant community made by ranging by hyperscalers to startups to academic institutions, hardware manufacturers, which are basically cooperating together and sharing experiences on to reduce risks, cutting down development costs, and avoiding even legal costs. So it's very important. But let's make a quick step back and have a look at the traditional 19-inch rack standard, also known as EIA 310D. The fun fact is that what we know as 19-inch rack standard basically has nothing which is 19-inch, except from the front plate of the devices. So it's just something. This standard dates back to the 1950s, coming from telephone signaling relays cabinets, which were very common at that time, and they came up with these standards. But this standard is coming very early in time, much before servers and computers were a thing. But since it was so useful and common to put boards, switches, and connectors, it was quickly picked up by the community, and it became the standards de facto also for computer systems and for servers. The rack unit, we also know now it as a standard, but it has only been standardized in 1992, so it's quite recently, and still after 40 years before the first standardization. And now, after almost 75 years from the first standard in 1950s, we can say that this model is starting to show up some weaknesses because we clearly lack physical space within the servers. There is no more room to host the components since CPUs are getting bigger and bigger. We need to put more and more DIMMs, and also we need to add GPUs, which are also becoming a bit bigger, fatter, thicker, and hotter, which brings us to the next problem. How do we cool those systems, which are getting hotter every day? Direct liquid cooling can definitely be a solution to address this problem, but adding cold plates everywhere with connectors on manifolds on the back of the servers, it's cumbersome and adds and overlaps to the already complex cable routing within the server itself. So it creates further challenges. That's why we need to find a complete different solution, and we have to start looking at the HPC and AI requirements with a complete different perspective and a different scale of approaching the problem. So besides looking at the 1U or 2U single rack server as the building block, we need to scale to the rack size to have a better approach and apply a better economy of scale. So, and this is where the approach of the Open Rack version 3 comes into play. This is a new relatively new specification proposed by the Open Compute project, just to overcome the limitations that we had in the previous specification, the EAIA 310. And it just defines the envelope and the interfaces between the various components, like power and cooling, leaving pretty much everything else to the implementation. So those can be, the other parameters can be customizable and configurable. So the key tenets of the Open Rack v3 specifications are the disaggregated power. Basically, we don't have any more PSUs within each rack, but we have power shelves serving the entire rack with a bus bar distributing the power across in the back of the chassis, distributing power to all the servers. We have an integrated liquid cooling solution, so we have manifolds in the back where the servers connect directly through blind maze, so it's a much more efficient way of connecting the system and to the liquid cooling, and we won't have a lot of cables hanging in the back. We have also a new form factor, because the Open Rack specification also introduced the new open unit, which is not the rack, it's slightly taller than the rack unit, which gives us a little bit more space to fit the components within the server, so we can allow for larger cold plates and more space. So, and the idea is that those devices, those new systems, will be serviced just from the front of from the cold aisle. So there is no need to go in the back of the server to plug cables and do stuff. And the other great thing is that we are doing exactly with the same cabinet footprint. We are not changing anything because basically the traditional cabinets have front and back flange mounts for mounting the devices on the vertical rails, but we have basically taken out those flanges and a little bit of the rails, and we are using wall mount clips to put the rails of each server, of each sled, and we are basically able to gain pretty much 3 inches. So from the 17.75, we are able to use 21 inches of width in a rack, which is more than 15%, which is great. With even without changing the footprint of the rack cabinet, which is great because we can still doing the same space allocation in our data centers as we used to do. So traditional racks also have typically traditional racks for HPC have 2, 4, or even 6 single or three-phase PDUs. Each server has multiple PSUs. We can reach up to 3.2 kilowatts per PSUs. Even if they have titanium efficiency and they are used in a redundant mode, which could be 1 plus 1, n plus 1, n plus n. This adds complexity and doesn't really scale well because there is a lot of over-provisioning in the PSUs. So when we put everything together in common factor and we use power shelves like you see in the right, it's much more efficient. With Open Rack V3 we have three-phase or direct current connecting directly to the back of the power shelves, and the distribution happens through the bus bar that you see depicted on the top of this slide. The power shelves have their own management so that you can configure the power, and they can sustain up to 33 kilowatts in n plus 1 mode, so they are already redundant. They have already integrated the automatic transfer switch, and they are able to balance automatically the power draw through the bus bar. So, and what you see in the bottom of the slide is the connector, which is within each server to get the power from the bus bar. The cooling is the other great thing of the Open Rack V3 specification, because we are using a mixture of 80% to 20% hybrid solution for liquid versus air cooling. But why is that? Because on high power compute systems, the biggest fraction of the heat, non-production heat, is produced just by the fan, by the spin of the fans. So power consumption of a fan is proportional to the cube of its rotational speed, and the fan speed, which basically governs the airflow, is proportional to the quantity of heat and air that can be removed from the CPUs, or, well, from the other components of the system. So the more we are able to drive that down, the better. And here I'm doing the case that even reducing by 20% the fan rotational speed, we are able to save up to 49%. So we are able to reduce much more significantly the rotational speed of the fans. So there is no need to try to cool everything with liquid, because it wouldn't be in any case that efficient. And also cooling would have overhead and would add additional cold plates that would be need to deploy on every DIMM, any disk, any NIC, and so on. So that will become a real nightmare for servicing those devices. So we still have a relatively simple server design, but with this hybrid cooling solution. So this is very important. Moving forward, we complete the liquid cooling solution with manifolds and these blind maze connections, because the Open Rack V3 specification also defines the shape and the position of those connectors. And on the market, there are basically two standards. One is the one that you see on the top is the universal quick disconnect blind mate, which allows only for vertical tolerance. And the one that you see on the bottom, it's the blind mate quick disconnect which is a slightly improved version with an additional O-ring in the connector, which allows even a radial tolerance, so it can be easier to deploy servers with those connectors. And these are, where is it? Okay, these are the caps that are used on the back of the servers. As you can see, this is the back of the servers. So you should imagine that when the server slides in, it fits and matches exactly perfectly the connectors in the back of the manifolds, and there is no need to have hanging connectors from the manifold going to the back of the server. So this is much more efficient solution. It completes the liquid cooling offering, also the capabilities of having a rear door heat exchanger or even heat capture cabinets, so we can have completely room neutral systems. So we can, and we are able to use this cabinet, the cabinet. I mean, this is just a drawing. It's not. It's still a concept, but the idea is that we can have a heat capture cabinet that can be HVW3 compliant, so it can cool an entire rack with just coolant at 32 degrees. So Open Rack V3 specification also has it's for servers, but we know that within a rack we still need to deploy other components which might not still be already Open Rack V3 compliant. So we have these trays and chunks which allows to put the traditional 19-inch rack like switches and so on. And we can power them with standard PSUs. The other component which we are missing so far in the list is the storage. Traditionally, this is still a problem on the specification, because the idea is to maximize, well, the basic design principle of storage devices is to maximize the usage of the front devices, of the front space to allow more disks, but this would conflict with the needs for the I/O in our computing environment. So this is where we are still struggling a little bit, and currently we have just a couple of prototypes, as you can see here, a server with a lot of storage in the front, or an attempt to design something with controllers in the back, but that would be a problem because it will interfere with the bus bar and the manifold. So storage is still not something that we have delivered, but we're still thinking. And now, well, this, just before leaving you, it's the Dell offering that we have currently in the Open Rack V3 specifications. We have basically three type of servers. Well, it's not servers, it's entire racks that can be delivered as a white glove service. We have the GPU only version, the CPU only version on the top that can scale up to 27,000, and I repeat, 27,000 AMD EPIC cores in a single rack with it. And as you can see, there is a huge computing power in this system. Then we have the GPU offering. We have the XE9712, which is based on the NVIDIA Grace CPU and Blackwell GPU in an NVL72 link configuration. This means that we have 72 GPUs in a single rack acting as a single huge super GPU for whatever you would like to do. And the last thing is the XE8712, which is a dense solution, just 10 open units, based on still on the NVIDIA Grace CPU, sorry, and it hosts four Blackwell GPUs connected in a four-way NVLink. So it's a relatively smaller scale, but it's still enormously powerful. And as the last slide, my 2 pennies, if you want to do data center planning for this new generation. Planning is key. You have to plan for the floor space. Maybe if you're looking for liquid cooling solution, you might need to have also the consider CDUs if you are thinking to deploy more than 3 servers, because those racks can host an internal CDU, but we have seen that the break-even point between the in-rack CDU and an in-row CDU is around the 3 racks. Power, of course, these guys are really hungry in terms of power. Be sure to have enough power to sustain those racks, because what we've seen, it's ranging around 150, 160 kilowatts per rack. So be sure to have enough power and enough redundancy for that. So that's all on my side. And if you have any questions. Somehow, yes. The manifolds have connectors for either in-rack CDU, or we can connect with an in-row CDU. So the way you decide to move the heat out of the room, it's up to the facility. It's not. We have engineered the heat closed cabinet to work with water up to 32 degrees. So this means that in a normal environment with the open loop, you might probably be looking even at slightly higher temperatures, but still you cannot bring the temperature too much higher.
Any other questions?
Thank you for your presentation. I just had a question regarding the liquid cooling going for the CPU and GPU, because even recently I was talking to people handling like HPC and cluster, and how do you come up or agree on this? Because some people are still reluctant to go for such an option.
So I didn't understand the questions.
Like, so my question is like, how can you like, how confident are you that liquid cooling, like the CPU and GPU, is safe? That you're not gonna get like an issue where like something has a leak and then destroys the entire rack?
We have all those servers have an embedded system management that controls the leaks. So in case of leaks, that they're spilling coolant on the surface, there is automatic shutdown. There are safety measures. But in any case, most of the liquid-cooled solutions are with negative pressure. This means that even if a cable, if a connector is cut, it already it seals itself.
Thank you.
You're welcome.
Thank you, Marco.
My pleasure.